Imagine standing at the edge of the observable universe, staring into the infinite darkness that stretches beyond our cosmic horizon. What lies out there in that unfathomable void? Are we alone in this vast expanse? Or are there countless other worlds, other civilizations, perhaps even other versions of ourselves existing in parallel realities? Today, we embark on an extraordinary journey through the cosmos, exploring the most mysterious and mind-bending phenomena that science has revealed about our universe. This journey will take us from the smallest quantum particles to the largest structures in existence, from the birth of time itself to the ultimate fate of everything we know. Our cosmic adventure begins with perhaps the most enigmatic objects in the universe, black holes. These gravitational monsters are so dense that nothing, not even light itself, can escape their grasp once it crosses the point of no return known as the event horizon. But what exactly is a black hole, and how do these cosmic vacuum cleaners form in the depths of space? The story of black holes begins with the life and death of stars, cosmic furnaces that have been burning in the darkness of space for billions of years. Stars are born in vast clouds of gas and dust called nebulae, where gravity slowly pulls material together until it becomes dense and hot enough for nuclear fusion to begin. For most of a star's life, this fusion process creates an outward pressure that balances the inward pull of gravity, maintaining the star in a stable state for millions or billions of years. Our Sun, a middle-aged star, has been burning hydrogen in its core for about 4.5 billion years and will continue to do so for roughly another 5 billion years before it begins to die. But for stars much more massive than our Sun, those containing at least 20 times more material, the story ends very differently. When these stellar giants exhaust their nuclear fuel, they can no longer support themselves against the relentless pull of gravity. The star's core collapses catastrophically in less than a second, releasing more energy in that brief moment than our Sun will produce in its entire 10 billion year lifetime. This collapse creates a region of space where the gravitational field is so intense that it warps the fabric of space-time itself, creating what Einstein's theory of general relativity describes as a singularity, a point where the known laws of physics break down and matter is compressed to infinite density. The event horizon surrounding this singularity acts like a cosmic boundary, a point of no return beyond which nothing can escape. The size of this boundary depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of only about 3 kilometers. For the supermassive black holes that lurk at the centers of galaxies, containing millions or billions of times the mass of our Sun, the event horizon can be larger than our entire solar system. Once anything crosses this threshold, it is doomed to fall toward the singularity, stretched and compressed by the immense tidal forces in a process scientists grimly call spaghettification. Imagine falling feet first toward a black hole. The gravitational pull on your feet would be significantly stronger than the pull on your head, stretching your body like a piece of spaghetti. These tidal forces become more extreme as you approach the singularity, eventually tearing apart anything that ventures too close, whether it's a spacecraft, a planet, or even individual atoms. From the outside universe's perspective, something even stranger happens due to the effects of Einstein's theory of relativity. Time dilation effects mean that anything falling into a black hole appears to slow down and freeze at the event horizon from the viewpoint of an external observer. The light from the falling object becomes increasingly redshifted, growing dimmer and redder until it fades from view entirely. To the outside universe, the object appears to be frozen at the event horizon forever, though from the falling object's perspective, it crosses the event horizon and reaches the singularity in a finite amount of proper time. But black holes are not just cosmic destroyers. They play a crucial role in shaping the universe around them, acting as cosmic architects that help build the large-scale structure we observe today. Supermassive black holes containing millions or billions of times the mass of our Sun lurk at the centers of nearly every galaxy, including our own Milky Way. These behemoths act as gravitational anchors, organizing the rotation of entire galaxies and influencing the formation of stars across cosmic distances. The supermassive black hole at our galaxy's center, known as Sagittarius A star, has a mass equivalent to 4 million suns and sits about 26,000 light-years from Earth. Despite its enormous mass, this black hole is relatively quiet compared to its more active cousins in other galaxies. We know it exists because we can observe stars orbiting around it at incredible speeds, some reaching velocities of thousands of kilometers per hour second as they whip around the invisible gravitational monster at the galactic center. In 2019, the Event Horizon Telescope achieved the impossible by capturing the first direct image of a black hole's event horizon. The target was not our own galactic black hole, but an even more massive one in the galaxy M87, located about 55 million light-years away. This black hole, with a mass of 6.5 billion suns, appears as a dark shadow surrounded by a glowing ring of superheated matter. The image confirmed many theoretical predictions about how black holes should appear and marked a historic milestone in astronomy. Recent discoveries have revealed that black holes are far from the silent, invisible objects they were once thought to be. When matter spirals into a black hole, it forms an accretion disk that heats up to millions of degrees due to friction and compression. This material glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays, making black holes some of the most luminous objects in the universe. The irony is striking. Black holes, which by definition cannot emit light, become visible through the brilliant glow of the matter they consume. Some black holes launch powerful jets of plasma at nearly the speed of light, creating cosmic lighthouses that can be seen across billions of light-years. These jets form when magnetic fields in the accretion disk become twisted and amplified, channeling some of the infalling matter into narrow beams that shoot out perpendicular to the disk. These relativistic jets can extend for thousands of light-years, influencing star formation in distant regions of their host galaxies and spreading heavy elements throughout intergalactic space. The study of black holes has led to some of the most profound questions in physics, challenging our understanding of information, causality, and the nature of reality itself. What happens to information that falls into a black hole? Does it disappear forever, violating fundamental principles of quantum mechanics, or is it somehow preserved? This puzzle, known as the black hole information paradox, has sparked decades of debate among physicists and led to revolutionary ideas about the nature of space, time, and reality itself. Stephen Hawking's groundbreaking work in the 1970s revealed that black holes actually emit radiation due to quantum effects near the event horizon. According to quantum mechanics, the vacuum of space is not truly empty, but filled with virtual particle pairs that pop in and out of existence. Near a black hole's event horizon, these virtual particles can become separated, with one particle falling into the black hole while the other escapes as real radiation. This Hawking radiation suggests that black holes slowly evaporate over time, eventually disappearing completely. The timescale for this evaporation is almost incomprehensibly long. For a black hole with the mass of our Sun, the evaporation process would take approximately 10 to the power of 67 years, a number so large that it dwarfs the current age of the universe by more than 50 orders of magnitude. Paradoxically, smaller black holes evaporate faster than larger ones, so hypothetical microscopic black holes would disappear almost instantly in a burst of radiation, while the supermassive black holes at galactic centers will persist long after all the stars in the universe have burned out. The implications of Hawking radiation are staggering. If this radiation carries no information about what fell into the black hole, then information could be destroyed when the black hole finally evaporates, challenging one of the fundamental assumptions of quantum mechanics. This creates a paradox because quantum mechanics insists that information must be conserved, while general relativity suggests that anything falling into a black hole is lost forever. Recent theoretical work by physicists like Leonard Susskind and others suggests that the information might be preserved after all, encoded in subtle correlations within the Hawking radiation itself. This resolution involves the holographic principle, which proposes that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. If true, this principle could revolutionize our understanding of reality, suggesting that our three-dimensional world might be an illusion projected from information encoded on a distant cosmic boundary. The holographic principle has far-reaching implications beyond black holes. It suggests that the universe might be fundamentally two-dimensional, with the third dimension of space emerging from the complex interactions of information on a cosmic boundary. This idea connects to string theory and the ADS/CFT correspondence, which relates theories of gravity in higher dimensional spaces to quantum field theories on lower dimensional boundaries. These connections hint at a deep unity in physics that we are only beginning to understand. Moving beyond black holes, let us explore another cosmic mystery that permeates the universe: dark matter. This invisible substance makes up approximately 27% of all matter and energy in the universe, yet we have never directly detected a single particle of it. Dark matter reveals its presence only through its gravitational effects on visible matter, bending light, influencing the rotation of galaxies, and providing the scaffolding upon which the large-scale structure of the universe is built. The story of dark matter begins in the 1930s with astronomer Fritz Zwicky, who was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. By measuring the speeds at which individual galaxies moved within the cluster, Zwicky could calculate how much mass was needed to hold the cluster together. What he found was shocking. The cluster contained far more mass than could be accounted for by the visible stars and gas. He called this missing mass dark matter, though it would be decades before the astronomical community took his discovery seriously. The evidence for dark matter became overwhelming in the 1970s when astronomer Vera Rubin studied the rotation curves of spiral galaxies. Just as planets in our solar system orbit more slowly the farther they are from the Sun, stars in the outer regions of galaxies should orbit more slowly than those near the center, following Kepler's laws of orbital mechanics. But Rubin's observations revealed something completely unexpected. Stars in the outer regions of galaxies were moving just as fast as those near the center, and in some cases even faster. This discovery implied that galaxies must contain much more mass than we can see, distributed in vast halos that extend far beyond the visible stars. Without this additional mass, the outer stars would fly off into space, unable to maintain their orbits around the galactic center. Computer simulations confirmed that galaxies simply could not exist in their observed forms without the gravitational scaffolding provided by dark matter. Further evidence comes from gravitational lensing, where massive objects bend the path of light from more distant sources. When astronomers observe distant galaxies through galaxy clusters, they often see multiple images of the same galaxy, distorted into arcs and rings by the gravitational field of the intervening cluster. By studying these distortions, astronomers can map the distribution of mass in the cluster, revealing vast amounts of invisible matter that outweighs the visible matter by a factor of 5 to 1. The cosmic microwave background radiation, the afterglow of the Big Bang, provides another crucial piece of evidence for dark matter. Tiny variations in the temperature of this radiation reveal the seeds of structure that eventually grew into galaxies and galaxy clusters. Computer. Simulations of cosmic evolution can only reproduce the observed patterns when dark matter is included in the calculations. Without dark matter, the universe would look completely different, with a much sparser distribution of galaxies and no large-scale structure. But what is dark matter made of? Despite decades of searching, this remains one of the greatest unsolved mysteries in science. The leading candidates are hypothetical particles that interact only weakly with ordinary matter, such as weakly interacting massive particles, or WIMPs. These particles would have been created in the early universe during the first moments after the Big Bang and would form vast halos around galaxies, providing the gravitational framework that allows ordinary matter to clump together and form stars and planets. WIMPs would be relics from the hot, dense early universe, when all types of particles were created and destroyed in a cosmic soup of energy. As the universe expanded and cooled, most of these exotic particles annihilated with their antiparticles, leaving only a small remnant that we observe as dark matter today. The predicted properties of WIMPs make them extremely difficult to detect, as they would pass through ordinary matter almost without interacting, like ghostly particles that inhabit the same space as regular matter but rarely make their presence known. Underground laboratories around the world house sensitive detectors designed to catch dark matter particles as they pass through Earth. These experiments must be shielded from cosmic radiation and other sources of interference, buried deep beneath mountains or in abandoned mines where the rock overhead filters out unwanted particles. The detectors themselves are marvels of engineering, containing ultra-pure crystals or liquids cooled to temperatures just above absolute zero, waiting for the rare collision between a dark matter particle and an atomic nucleus. So far, no confirmed detection has been made, but each negative result helps narrow down the possible properties of dark matter particles and guides the construction of even more sensitive detectors. Some experiments have reported tantalizing hints of dark matter signals, but these results remain controversial and have not been independently confirmed. The search continues with ever more sophisticated detectors, each one capable of detecting smaller and smaller interactions. Alternative theories propose that dark matter might not be particles at all, but instead a modification to our understanding of gravity itself. These modified gravity theories, such as modified Newtonian dynamics, or MOND, suggest that the laws of physics behave differently on cosmic scales than they do in our solar system. In this view, the apparent effects of dark matter result from our incomplete understanding of how gravity works over vast distances, eliminating the need for exotic particles. However, modified gravity theories struggle to explain all the observations that dark matter explains so naturally. While they can account for galaxy rotation curves, they have difficulty explaining gravitational lensing observations, the cosmic microwave background radiation background, and the large-scale structure of the universe. Most physicists favor the dark matter explanation, but the continued failure to detect dark matter particles keeps alternative theories in consideration. Other dark matter candidates include axions, hypothetical particles that were originally proposed to solve problems in the theory of quantum chromodynamics. Axions would be incredibly light, billions of times lighter than electrons, but could be produced in such vast quantities that they account for all the dark matter in the universe. Detecting axions would require different experimental techniques than those used to search for WIMPs, involving powerful magnetic fields and sensitive microwave detectors. Sterile neutrinos represent another possibility. Regular neutrinos are known to exist and have a tiny but non-zero mass, but they are too light to account for all the dark matter. Sterile neutrinos would be heavier cousins of regular neutrinos that interact even more weakly with ordinary matter. These particles could be produced in the early universe and might explain some puzzling observations in neutrino physics experiments. Even more exotic possibilities include primordial black holes, which could have formed in the early universe from extremely dense regions that collapsed under their own gravity. These black holes would be much smaller than those formed from stellar collapse, potentially ranging from microscopic sizes to masses comparable to planets or stars. If they exist in sufficient numbers, primordial black holes could account for some or all of the dark matter, though current observations place strict limits on their abundance. The search for dark matter has driven technological innovation and international collaboration on an unprecedented scale. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions, while space-based telescopes search for the gamma rays that might be produced when dark matter particles annihilate. Underground laboratories on multiple continents compete and collaborate to achieve the sensitivity needed to detect these elusive particles. Even more mysterious than dark matter is dark energy, which makes up approximately 68% of the universe and drives its accelerating expansion. This cosmic phenomenon was discovered in 1998 when two independent teams of astronomers studying distant supernovae found that the universe's expansion is speeding up rather than slowing down as expected. This discovery was so unexpected that it earned the leaders of both teams the Nobel Prize in Physics in 2011. The story begins with Type 1a supernovae, which serve as cosmic lighthouses because they all reach approximately the same peak brightness. These stellar explosions occur when a white dwarf star, the dense remnant of a dead star, accretes material from a companion star until it reaches a critical mass and explodes. Because the trigger for these explosions is always the same, Type 1a supernovae can be used as standard candles to measure distances across cosmic scales. By comparing the observed brightness of distant supernovae to their known intrinsic brightness, astronomers can calculate their distances. By measuring the redshift of light from the host galaxies, they can determine how fast these galaxies are receding from us due to the expansion of the universe. The relationship between distance and recession velocity reveals the history of cosmic expansion and allows astronomers to determine whether the expansion is accelerating or decelerating. What the supernova teams found was completely unexpected. Distant supernovae appeared dimmer than they should be if the universe's expansion was slowing down due to the gravitational pull of matter. Instead, the observations indicated that the expansion is accelerating, as if some mysterious force is pushing space apart on the largest scales. This acceleration requires a form of energy that permeates all of space and exerts a repulsive gravitational effect. The nature of dark energy is completely unknown and represents perhaps the deepest mystery in cosmology. It might be a property of space itself, a quantum field that fills the universe, or something far stranger that we have not yet imagined. The leading candidate is the cosmological constant, a term that Einstein originally introduced into his equations to allow for a static universe, but later called his greatest blunder when the expansion of the universe was discovered. The cosmological constant would represent the energy density of empty space itself, arising from quantum fluctuations that give the vacuum a non-zero energy. However, when physicists attempt to calculate what this vacuum energy should be using quantum field theory, they get an answer that is larger than the observed value by more than 120 orders of magnitude. This represents perhaps the worst prediction in the history of physics and highlights our complete lack of understanding about the nature of dark energy. Alternative models propose that dark energy might be a dynamic field that changes over time, similar to the field that drove cosmic inflation in the early universe. This quintessence field would have different properties from the cosmological constant, potentially allowing it to vary in strength or even change sign, switching from repulsive to attractive. Some models suggest that dark energy might interact with dark matter, creating a rich phenomenology that could explain various puzzles in cosmology. The implications of dark energy are profound and disturbing. If the acceleration continues unchanged, the universe will eventually enter a phase called the Big Rip, where the expansion becomes so rapid that it overcomes all other forces, tearing apart galaxies, stars, planets, and eventually atoms themselves. In this scenario, the universe would end not with a whimper, but with a catastrophic dissolution of all structure, occurring in a finite time in the far future. Alternatively, dark energy might change over time, possibly reversing the expansion and leading to a big crunch where the universe collapses back on itself. Or it might decay away entirely, leaving behind a universe that expands forever but at a decelerating rate. The ultimate fate of the universe depends critically on the nature of dark energy, making its study one of the most important goals in cosmology. Recent observations have begun to constrain the properties of dark energy more precisely. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and other large-scale projects are mapping millions of galaxies to measure how the expansion rate of the universe has changed over time. These observations will help distinguish between different models of dark energy and might reveal clues about its fundamental nature. The combination of dark matter and dark energy means that the ordinary matter we see around us, the stars, planets, and everything made of atoms, comprises only about 5% of the universe. We live in a cosmos dominated by invisible, mysterious components that we barely understand. This realization has humbled astronomers and physicists, reminding us how much we still have to learn about the universe we inhabit. Our exploration of cosmic mysteries leads us next to one of the most fundamental questions in astronomy. Are we alone in the universe? The search for extraterrestrial life has captured human imagination for centuries, but only recently have we developed the tools and techniques to seriously investigate this question. The discovery of thousands of planets orbiting other stars has revealed that planetary systems are common throughout the galaxy, with potentially habitable worlds existing in the billions. The modern search for exoplanets began in 1995 with the discovery of 51 Pegasi b, the first planet found orbiting a Sun-like star. This Jupiter-sized world orbits incredibly close to its star, completing an orbit in just 4 days and reaching temperatures hot enough to melt metal. The existence of such hot Jupiters came as a complete surprise, as our solar system contains no planets in such extreme orbits. This discovery revolutionized our understanding of planetary formation and migration. Since then, astronomers have discovered over 5,000 confirmed exoplanets using various detection techniques. The transit method watches for the tiny dimming that occurs when a planet passes in front of its star as seen from Earth. The radial velocity method detects the wobble that a planet's gravity induces in its star. Direct imaging attempts to photograph planets directly, while gravitational microlensing uses the bending of light to reveal planets around distant stars. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science by monitoring over 100,000 stars simultaneously, looking for the periodic dimming caused by transiting planets. Kepler's observations revealed that planets are extremely common, with most stars hosting at least one planet and many systems containing multiple worlds. The telescope discovered planets ranging from super-Earths, twice the size of our world, to gas giants larger than Jupiter, in orbits ranging from hellishly hot to frozen and distant. One of Kepler's most important discoveries was that Earth-sized planets in the habitable zones of their stars are relatively common. The habitable zone, sometimes called the Goldilocks zone, represents the range of distances from a star where liquid water can exist on a planet's surface. This zone is neither too hot nor too cold, but just right for the chemistry of life as we know it. Within our own solar system, Earth sits comfortably in this zone, Mars lies near its outer edge, and Venus is too close to the Sun, suffering from a runaway greenhouse effect. However, being in the habitable zone is just one of many factors that determine whether a planet can support life. The planet needs to have the right mass to retain an atmosphere, the right atmospheric composition to maintain liquid water, and protection from harmful radiation. It likely needs a large moon to stabilize its rotation and climate, active geology to recycle carbon and maintain plate tectonics, and a magnetic field to shield it from cosmic rays and stellar winds. Recent discoveries have expanded our understanding of where life might exist beyond the traditional habitable zone. Jupiter's moon Europa and Saturn's moon Enceladus both harbour subsurface oceans beneath their icy crusts, potentially containing more liquid water than all of Earth's oceans combined. These moons are heated by tidal forces from their giant parent planets, creating environments that might support microbial life, even in the outer solar system where sunlight is weak. Europa's subsurface ocean is thought to be in contact with the moon's rocky mantle, potentially providing the chemical nutrients that life requires. Hydrothermal vents on the ocean floor, similar to those found in Earth's deep oceans, could provide energy sources for exotic forms of life that do not depend on sunlight. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will study this intriguing world in detail and search for signs of biological activity. Enceladus has already provided tantalizing evidence of a potentially habitable environment. The Cassini spacecraft detected water vapor and organic molecules in the plumes that erupt from the moon's south pole, suggesting that its subsurface ocean has the basic ingredients for life. Future missions might be able to sample these plumes directly, searching for biosignatures without needing to land on the surface. Other moons in our solar system also show promise for harboring life. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface and a subsurface ocean of water. While methane-based life is highly speculative, Titan's complex chemistry and abundant organic molecules make it an intriguing target for astrobiological investigation. Jupiter's moons, Ganymede and Callisto, also likely harbour subsurface oceans, though they are less well studied than Europa. The James Webb Space Telescope has revolutionized the search for potentially habitable worlds by analyzing the atmospheres of distant planets as they pass in front of their host stars. By studying the spectrum of starlight filtered through these atmospheres, astronomers can identify the presence of water vapor, oxygen, methane, and other gases that might indicate biological activity. The telescope has already characterized the atmospheres of numerous exoplanets, revealing worlds with clouds, weather systems, and chemical compositions that provide clues about their potential habitability. One of the most promising targets is the TRAPPIST-1 system, located just 39 light-years from Earth. This red dwarf star hosts 7 Earth-sized planets, 3 of which orbit in the habitable zone. The planets are so close together that if you stood on the surface of one, the others would appear larger in the sky than our moon. The James Webb Space Telescope is studying these worlds in detail, searching for signs of atmospheres and potentially habitable conditions. But the search for life extends beyond just finding habitable conditions. The field of astrobiology investigates how life might arise and evolve under different circumstances, studying extremophile organisms on Earth that thrive in conditions once thought impossible for life. These hardy microbes live in boiling hot springs, highly acidic environments, deep underground, and even in the vacuum of space, suggesting that life might be far more adaptable and widespread than previously imagined. Some extremophiles survive in environments with no oxygen, deriving energy from chemical reactions involving sulfur, methane, or hydrogen. Others thrive in extremely salty conditions, high radiation environments, or temperatures near the boiling point of water. The discovery of life in such extreme conditions has expanded the range of environments where astronomers search for extraterrestrial life and has implications for the early evolution of life on Earth. The study of extremophiles has also informed our understanding of what biosignatures we should look for in exoplanet atmospheres. Oxygen is often considered the gold standard biosignature because it is highly reactive and would quickly disappear from an atmosphere unless continuously replenished by biological processes like photosynthesis. However, extremophiles suggest that life might produce other detectable gases, such as phosphine, hydrogen sulfide, or various organic compounds. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. This equation considers factors such as the rate of star formation, the fraction of stars with planets, the number of planets in habitable zones, the fraction where life develops, the likelihood that life evolves intelligence, the probability that intelligent life develops technology, and the length of time such civilizations release detectable signals into space. While many of these factors remain highly uncertain, recent discoveries have begun to provide better estimates for some terms in the equation. We now know that planets are common, with most stars hosting planetary systems. We also know that potentially habitable planets exist in significant numbers, though we are still learning how many of them actually possess the conditions necessary for life. The fraction of habitable planets where life actually emerges remains completely unknown, as we have only one example: Earth. The search for extraterrestrial intelligence, or SETI, uses radio telescopes to listen for artificial signals from alien civilizations. The assumption is that any technological civilization would inevitably discover radio waves and might use them for communication, either intentionally sending messages to other stars or inadvertently leaking radio signals into space through their technology. SETI searches scan millions of stars, looking for narrowband signals or other patterns that would indicate an artificial origin. Despite decades of searching, SETI has found no confirmed signals from extraterrestrial intelligence. This null result raises questions about the abundance of intelligent life in the galaxy and has led to various explanations for the apparent silence of the cosmos. Perhaps intelligent life is extremely rare, or perhaps technological civilizations tend to destroy themselves before developing interstellar communication capabilities. Alternatively, alien civilizations might use communication technologies that we have not yet discovered, or might be deliberately avoiding contact with primitive civilizations like ours. The Fermi paradox, named after physicist Enrico Fermi, poses a troubling question. If the conditions for life are common, and the universe is so vast and old, where is everybody? This paradox highlights the apparent contradiction between the high probability of extraterrestrial life suggested by the Drake equation and our complete lack of evidence for its existence. The paradox has spawned numerous proposed solutions, each with different implications for our place in the universe. One possibility is that we are among the first intelligent civilizations to arise in our galaxy. If life is common but intelligence is rare, we might be living during a special time when the universe is just beginning to wake up to its own existence. This solution suggests that we might be destined to become one of the elder civilizations that future intelligences will look back on as pioneers in the exploration of the cosmos. Another explanation is the Great Filter hypothesis, which proposes that there is some extremely difficult evolutionary step that prevents most life from developing into spacefaring civilizations. This filter might be the origin of life itself, the evolution of eukaryotic cells, the development of multicellular organisms, the emergence of intelligence, or the development of technology. If the Great Filter lies in our past, we might be among the lucky few who have successfully passed through it. If it lies in our future, our prospects might be grim. The zoo hypothesis suggests that advanced alien civilizations are aware of us, but are deliberately avoiding contact, perhaps observing us like specimens in a zoo, or waiting for us to reach a certain level of technological or social development before making contact. This explanation preserves the possibility of abundant alien life, while explaining why we have not encountered it directly. More disturbing possibilities include the idea that intelligent civilizations tend to destroy themselves through warfare, environmental destruction, or other catastrophes, or that they inevitably develop technologies that make them withdraw from the physical universe into virtual realities or other forms of existence that we cannot detect. These scenarios suggest that intelligence might be common but short-lived, leaving behind only ruins or subtle traces of their former existence. Recent developments in our understanding of planetary atmospheres and climate have revealed new potential filters for life. The discovery that Venus likely had oceans for billions of years before suffering a runaway greenhouse effect suggests that apparently habitable planets might lose their habitability due to climate instability. Similarly, the realization that Earth's climate has been precariously balanced throughout its history suggests that maintaining habitable conditions might be more difficult than previously thought. The possibility of finding fossilized life on Mars has generated enormous excitement in recent years. Several Mars missions have found evidence that the red planet once had liquid water on its surface, with ancient riverbeds, lake deposits, and mineral formations that require water to form. The Perseverance rover is currently collecting rock samples that might contain fossilized microbes from Mars' wetter past, with plans to return these samples to Earth for detailed analysis in the 2030s. If life existed on Mars billions of years ago, it would prove that life can arise independently in multiple locations, suggesting that the universe might be teeming with living worlds. Even if Martian life is extinct, its discovery would revolutionize astrobiology and provide crucial insights into how life begins and evolves under different conditions. The possibility remains that life might still exist in subsurface environments on Mars, protected from the harsh radiation and extreme cold of the surface. One of the most intriguing possibilities is that we are living in a computer simulation created by a more advanced civilization. This simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that what we perceive as reality is actually a sophisticated computer program, and we are either artificial intelligences within that program or conscious minds interfaced with it. While this idea sounds like science fiction, some philosophers and scientists argue that it deserves serious consideration, especially given the rapid advancement of our own computational capabilities. The argument for the simulation hypothesis rests on several assumptions about the development of advanced civilizations. If a civilization develops sufficient computational power, they might choose to run detailed simulations of their ancestors or other aspects of their history. If such simulations are possible and desirable, there might be many more simulated beings than real ones, making it statistically more likely that we are among the simulated rather than the real. Evidence for the simulation hypothesis is difficult to identify, as a sophisticated simulation would be indistinguishable from reality to its inhabitants. Some proposed tests include looking for glitches or computational shortcuts that might reveal the underlying digital nature of reality, but such evidence would be extremely subtle and difficult to distinguish from our incomplete understanding of physical laws. Whether we are real or simulated, biological or artificial, alone or surrounded by alien civilizations, the implications of our cosmic situation are profound. The discovery of extraterrestrial life, even in microbial form, would revolutionize our understanding of biology, evolution, and our place in the universe. It would prove that life can arise independently in multiple locations, suggesting that the cosmos might be rich with living worlds, and that we are part of a vast community of life that spans the universe. The discovery of intelligent extraterrestrial life would raise even more profound questions about consciousness, technology, and the future evolution of intelligence in the universe. It would force us to confront questions about our own intelligence, our technology, and our responsibility as potentially one of many intelligent species in the cosmos. Such a discovery might unite humanity in ways that no previous event in our history has achieved, giving us a cosmic perspective on our existence and our future. Our cosmic journey now takes us to the very beginning of time itself, to explore the origin and early evolution of the universe. The Big Bang Theory provides our best understanding of how the universe began approximately 13.8 billion years ago, not as an explosion in space, but as the expansion of space itself from an initial state of extreme density and temperature. This theory represents one of the greatest intellectual achievements in human history, unifying our understanding of the cosmos from the smallest scales to the largest. The evidence for the Big Bang is overwhelming and comes from multiple independent observations. The cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, provides a snapshot of the universe when it was only 380,000 years old and first became transparent to light. This radiation fills all of space with nearly perfect uniformity, but tiny variations in its intensity reveal the seeds of structure that would eventually grow into galaxies and galaxy clusters. The cosmic microwave background represents the afterglow of the Big Bang, stretched and cooled by billions of years of cosmic expansion. When it was emitted, this radiation had a temperature of about 3000 Kelvin, hot enough to ionize hydrogen and make the universe opaque to light. As the universe expanded, this radiation cooled and redshifted until today it has a temperature of just 2.7 Kelvin above absolute zero, appearing as microwave radiation that fills the entire observable universe. The nearly perfect uniformity of this background radiation was initially puzzling because regions of the universe that are now separated by billions of light years would not have had time to communicate with each other when the radiation was emitted. How could these distant regions have reached the same temperature without some mechanism to equilibrate them? This puzzle led to the development of cosmic inflation theory, which we will explore in detail shortly. The observed abundance of light elements in the universe provides another crucial piece of evidence for the Big Bang. Big Bang nucleosynthesis, occurring during the first few minutes after the Big Bang, produced the primordial hydrogen and helium that make up most of the normal matter in the universe. The nuclear reactions during this epoch were determined by the temperature, density, and expansion rate of the early universe, allowing physicists to make precise predictions about the ratios of different light elements that should be observed today. These predictions match observations with remarkable precision. Roughly 75% of normal matter consists of hydrogen, about 25% is helium-4, and trace amounts of deuterium, helium-3, and lithium are observed in exactly the proportions predicted by Big Bang nucleosynthesis. This agreement represents one of the most precise confirmations of the Big Bang theory and provides strong evidence that the universe was indeed much hotter and denser in the past. But the Big Bang theory raises as many questions as it answers. What caused the Big Bang? What, if anything, existed before it? Why does the universe have the specific properties we observe rather than some other configuration? Why is the universe so uniform on large scales, and why does space appear to be geometrically flat rather than curved? These profound questions have driven theoretical physicists to develop extensions and modifications of the basic Big Bang model. The theory of cosmic inflation, developed in the 1980s by Alan Guth and refined by André Linde, André Albrecht, and others, addresses many of these puzzles by proposing that the universe underwent a period of exponential expansion during its first fraction of a second of existence. During inflation, the universe expanded faster than the speed of light, growing by a factor of at least 10 to the 26th power in less than 10 to the minus 32 seconds. This extraordinary expansion explains why the universe appears so uniform on large scales. Regions that are now separated by billions of light years were once close enough together to reach thermal equilibrium before inflation stretched them apart. It also explains why space appears to be geometrically flat, as inflation would stretch any initial curvature until it becomes undetectable, much like the surface of a balloon appears flat when inflated to enormous size. Inflation also provides a mechanism for generating the tiny quantum fluctuations that seeded the formation of all cosmic structure. According to quantum mechanics, empty space is filled with virtual particles that pop in and out of existence on extremely short timescales. During inflation, these quantum fluctuations were stretched to macroscopic scales and frozen as density perturbations that later grew under the influence of gravity to form galaxies and galaxy clusters. The predictions of inflation theory have been confirmed by increasingly precise measurements of the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have mapped the tiny temperature variations in this background radiation with exquisite precision, revealing patterns that match the predictions of inflation theory. These observations have established inflation as the standard paradigm for early universe cosmology. However, inflation theory also leads to some of the most radical ideas in modern physics. If inflation can occur once, it can presumably occur multiple times, leading to the concept of eternal inflation. In this scenario, inflation never completely ends, but continues in some regions of space while ending in others. Each region where inflation ends becomes a separate universe, creating a vast multiverse of bubble universes expanding within an ever-inflating background. This multiverse theory suggests that our observable universe might be just one of countless universes that exist in a vast cosmic ensemble. Different universes in this multiverse might have different physical laws, different values for fundamental constants like the strength of gravity or the mass of the electron, and entirely different properties. Some universes might be dominated by black holes, others might contain only radiation, and still others might have physical laws so different that no complex structures can form at all. The multiverse concept provides a potential explanation for why our universe appears to be fine-tuned for the existence of complexity and life. The fundamental constants of nature seem to be precisely calibrated to allow for the formation of atoms, stars, planets, and ultimately life itself. If any of these constants were significantly different, the universe would be a very different and likely uninhabitable place. For example, if the strong nuclear force were slightly weaker, atomic nuclei would not be stable and only hydrogen would exist. If it were slightly stronger, hydrogen would not exist because protons would bind together too easily, preventing the formation of stable atoms. If the electromagnetic force were much stronger, electrons would be bound too tightly to atomic nuclei to participate in chemical reactions. If gravity were much stronger, stars would burn out too quickly for life to evolve. The anthropic principle attempts to explain these apparent coincidences by noting that we necessarily observe a universe compatible with our existence. In a multiverse where all possible values of fundamental constants are realized, intelligent observers will inevitably find themselves in universes with parameters that allow for complexity and life. This explanation is controversial because it seems to give up on finding deeper physical reasons for the values of fundamental constants. The strong anthropic principle suggests that the universe must have properties that allow intelligent life to develop, while the weak anthropic principle simply notes that we observe a life-friendly universe because we could not exist in one that was hostile to life. The distinction between these versions has important implications for how we understand our place in the cosmos and whether our universe is special in any fundamental sense. Critics of the multiverse argue that it is unscientific because it cannot be tested or falsified by observation. If other universes are causally disconnected from ours, we can never observe them directly or gather evidence for their existence. This has led some physicists to argue that the multiverse is more philosophy than science, though others contend that it is a natural consequence of our best theories of inflation and quantum mechanics. Recent work has focused on finding indirect evidence for the multiverse through signatures that might be imprinted on our observable universe. If our universe had collided with another universe in the distant past, such a collision might leave detectable traces in the cosmic microwave background radiation. Searches for such signatures have so far come up empty, but the techniques continue to improve. String theory, our best candidate for a theory of quantum gravity, also naturally leads to multiverse scenarios. String theory requires extra dimensions beyond the 3 spatial dimensions we experience, and the way these extra dimensions are compactified determines the physical properties of the resulting 4-dimensional universe. There appear to be an enormous number of possible compactifications, each leading to a different set of physical laws and constants. This string landscape might contain 10 to the 500th power different vacuum states, each corresponding to a different possible universe with its own laws of physics. If eternal inflation populates this landscape by creating universes corresponding to different vacuum states, the result would be a multiverse of staggering diversity, with our universe being just one random sample from an almost infinite variety of possibilities. As we peer deeper into space and further back in time, we approach the limits of what is observable from our cosmic vantage point. The observable universe has a finite radius of approximately 46 billion light-years, representing the maximum distance from which light has had time to reach us since the Big Bang. This might seem counterintuitive since the universe is only 13.8 billion years old, but the expansion of space means that objects we see today are much farther away now than they were when they emitted the light we observe. Beyond this cosmic horizon lies the unobservable universe, which may be vastly larger than what we can see. If the universe is infinite in extent, as many models suggest, then the observable universe represents an infinitesimally small fraction of total reality. This unobservable region might contain countless galaxies, stars, and possibly even other intelligent civilizations that we can never hope to detect because their light has not had time to reach us. The cosmic microwave background radiation represents the surface of last scattering, the moment when the universe became transparent to photons for the first time. Before this epoch, which occurred about 380,000 years after the Big Bang, the universe was opaque to electromagnetic radiation, filled with a hot plasma of electrons and nuclei that scattered photons before they could travel very far. We cannot observe the universe directly before this time using conventional telescopes, but gravitational wave detectors might eventually allow us to probe even earlier epochs. Gravitational waves from the early universe would have propagated freely since the first moments after the Big Bang, potentially carrying information about cosmic inflation, phase transitions, and other exotic processes that occurred when the universe was less than a second old. The Laser Interferometer, Gravitational Wave Observatory, LIGO, and its European counterpart Virgo have already detected gravitational waves from merging black holes and neutron stars, opening an entirely new window on the universe. Future space-based detectors like the Laser Interferometer Space Antenna, LISA, will be sensitive to different frequencies of gravitational waves, potentially detecting signals from the early universe that could provide direct evidence for cosmic inflation. Recent observations have revealed that the large-scale structure of the universe resembles a cosmic web, with galaxies arranged along filaments separated by vast voids. This structure emerged from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Computer simulations can reproduce this cosmic web in remarkable detail, showing how dark matter formed the scaffolding upon which ordinary matter condensed to form galaxies and stars. The largest structures in the universe, such as the Great Wall of Galaxies and the Botez Void, span hundreds of millions of light-years and represent the limits of how clumpy matter can become under the influence of gravity and dark energy. These structures are so large that they challenge our understanding of cosmic evolution, as there may not have been enough time since the Big Bang for gravity to assemble such massive concentrations of matter. The discovery of these enormous structures has led to new questions about the fundamental nature of the universe. Some observations suggest that the universe might not be as uniform on the larger scales as the standard cosmological model predicts. The cosmic microwave background appears slightly more varied in one direction than in others, and the distribution of distant galaxies shows hints of unexpected patterns that might indicate new physics beyond our current understanding. The ultimate fate of the universe depends on the nature of dark energy and whether its effects change over time. In the most likely scenario, based on current observations, the universe will continue expanding and cooling, eventually becoming a cold, dark, and empty place where all the stars have burned out and black holes have evaporated away through Hawking radiation. This heat death represents the maximum entropy state of the universe, where no more work can be done and no new structures can form. The timeline for this cosmic ending is almost incomprehensibly long. Stars will continue forming for perhaps another trillion years before the supply of hydrogen is exhausted. Red dwarf stars, the most common type, can burn for trillions of years more. After all the stars have died, the universe will be dominated by black holes, which will slowly evaporate through Hawking radiation over timescales that make the current age of the universe seem like an instant. The largest black holes will take approximately 10 to the 100th power years to evaporate completely. After this unimaginably long time, the universe will contain only a thin gas of elementary particles, gradually spreading apart as space continues to expand. Even protons might eventually decay, though this process has never been observed and would take at least 10 to the 34th power years if it occurs at all. Alternatively, if dark energy weakens or reverses, the expansion might eventually halt and reverse, leading to a big crunch where all matter and energy collapse back into a singularity. This scenario would see the cosmic web collapse, galaxies merge, and eventually all matter crushed back into the extremely hot, dense state from which the universe emerged. The timescale for such a collapse would depend on how quickly dark energy changes, but it could occur anywhere from tens of billions to trillions of years in the future. Some theories propose cyclical cosmologies where the universe undergoes repeated cycles of expansion and contraction, potentially lasting for eternity. In these models, each cycle might reset the laws of physics or the values of fundamental constants, creating an eternally cycling multiverse where every possible universe is eventually realized. These cyclical models avoid the problem of a beginning or ending to time, but face challenges in explaining how information and entropy are handled across cycles. Other models suggest that the universe might undergo phase transitions that fundamentally alter the laws of physics, creating entirely new types of structure and complexity. These phase transitions could be triggered by quantum tunneling events or changes in the vacuum state of fundamental fields, potentially leading to regions of space with completely different physical properties. The possibility of vacuum decay represents one of the most disturbing scenarios for the far future. The Higgs field that gives particles their mass might exist in a metastable state rather than the true ground state of the universe. If this false vacuum decays, it would create a bubble of true vacuum that expands at the speed of light, destroying all matter and rewriting the laws of physics in its wake. Current calculations suggest that such a vacuum decay event would be extraordinarily unlikely over the age of the universe, but the possibility cannot be completely ruled out. If it occurs, there would be no warning, as the bubble of true vacuum would approach us at the speed of light, destroying everything in its path and creating a fundamentally different universe with new physical laws. Despite these potentially grim scenarios for the far future, some physicists have speculated about whether intelligent civilizations might find ways to survive even the heat death of the universe. Freeman Dyson proposed that advanced civilizations might slow down their computational processes to match the decreasing energy available as the universe expands and cools, potentially allowing consciousness to persist indefinitely even in a dying universe. Other speculative scenarios involve escaping to other universes through wormholes or quantum tunneling events, or even creating new universes through advanced technology. While these ideas remain purely speculative, they represent attempts to find hope even in the face of cosmic doom, suggesting that intelligence might find ways to transcend the physical limitations of our universe. Our exploration of cosmic mysteries brings us to the cutting edge of physics, where scientists are working to understand the deepest levels of reality and unify our understanding of the fundamental forces of nature. The quest for a theory of everything represents one of the greatest intellectual challenges in human history, attempting to reconcile the quantum mechanical description of the very small with Einstein's general relativistic description of gravity and space-time. String theory, our most promising candidate for such a unification, proposes that the fundamental particles we observe are not point-like objects, but tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience. These strings are unimaginably small, with lengths on the order of the Planck length, approximately 10 to the minus 35 meters. At such scales, the distinction between particles and forces breaks down, replaced by different vibrational modes of the fundamental strings. Different vibrational patterns of these strings correspond to different particles, potentially unifying all the fundamental forces of nature in a single theoretical framework. A string vibrating in one pattern might appear as an electron, while the same string vibrating in a different pattern could manifest as a photon or a graviton. This elegant unification suggests that all the complexity of particle physics emerges from the simple dynamics of vibrating strings in higher dimensional space. String theory requires the existence of extra dimensions that are compactified or curled up so small that we cannot detect them directly with current technology. While we experience 3 spatial dimensions, string theory typically requires 6 or 7 additional spatial dimensions for a total of 9 or 10 dimensions of space plus 1 dimension of time. These extra dimensions might be rolled up in complex geometric shapes called Calabi-Yau manifolds, with the specific geometry determining the physical properties of our observable 4-dimensional world. The compactification of these extra dimensions might explain why gravity is so much weaker than the other fundamental forces. While electromagnetic, weak and strong forces are confined to our 3-dimensional space, gravity might propagate through all the extra dimensions, diluting its strength in our observable world. This could explain why gravity is about 10 to the 40th power times weaker than electromagnetism, despite being the force that dominates on cosmic scales. Some versions of string theory predict the existence of parallel brane worlds, where our entire universe exists on a 3-dimensional surface called a brane embedded in higher dimensional space. Other branes might exist nearby in the extra dimensions, hosting their own universes with potentially different physical laws. These parallel universes might interact with ours only through gravity, which can propagate through the extra dimensions, possibly explaining some of the mysteries of dark matter and dark energy. The brane world scenario suggests that what we perceive as dark matter might actually be ordinary matter on a nearby parallel brane, whose gravitational effects we can feel but which remains invisible because light cannot travel between branes. Similarly, dark energy might result from the interaction between our brane and others, or from the expansion of the extra dimensions themselves. Loop quantum gravity offers an alternative approach to quantum gravity, suggesting that space and time themselves are quantized at the smallest scales rather than being continuous as assumed in general relativity. According to this theory, space consists of discrete loops and nodes that form a quantum foam at distances smaller than the Planck length, approximately 10 to the minus 35 meters. This quantization of spacetime might resolve the singularities that plague general relativity, such as those found at the centers of black holes or at the beginning of the Big Bang. In loop quantum gravity, these singularities are replaced by quantum bounces, where matter reaches a maximum density before rebounding. This suggests that the Big Bang might actually have been a big bounce, where a previous contracting universe rebounded into the expansion we observe today. The holographic principle, which emerged from studies of black hole thermodynamics, suggests that all the information contained within a region of space can be encoded on its boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. This principle has led to the ADS/CFT correspondence, which relates theories of gravity in higher dimensional anti-de Sitter spaces to conformal field theories on lower dimensional boundaries. This correspondence has provided powerful tools for studying both quantum gravity and strongly coupled quantum field theories, allowing physicists to translate difficult problems in one framework into more tractable problems in the other. It suggests that our three-dimensional reality might actually be a holographic projection from information encoded on a distant two-dimensional surface, fundamentally changing our understanding of the nature of space and reality. The holographic principle has profound implications for our understanding of information and entropy. If all the information in a region of space can be encoded on its boundary, then the maximum entropy of that region is proportional to the area of the boundary rather than the volume. This explains why black holes have entropies proportional to their surface areas and provides insights into the fundamental nature of information storage in the universe. Quantum entanglement, which Einstein famously called spooky action at a distance, reveals non-local correlations between particles that appear to violate our classical notions of space and time. When two particles become quantum entangled, measuring one instantly affects the state of the other, regardless of the distance separating them. This phenomenon suggests that the universe might be fundamentally non-local, with connections that transcend the limitations of space-time. Recent experiments have demonstrated quantum entanglement over increasingly large distances, with entangled particles maintaining their correlations across hundreds of kilometers. These experiments have potential applications for quantum communication and computing, but they also raise profound questions about the nature of reality and whether space and time are as fundamental as we typically assume. Some theories suggest that quantum entanglement might be responsible for the emergence of space-time itself. The idea is that the geometry of space arises from patterns of quantum correlation between fundamental degrees of freedom, with more highly entangled regions corresponding to smaller distances in the emergent space-time. This represents a complete reversal of our usual thinking, where quantum mechanics emerges from space-time rather than space-time emerging from quantum mechanics. The measurement problem in quantum mechanics raises fundamental questions about the nature of reality and the role of consciousness in physical processes. According to the standard Copenhagen interpretation, quantum systems exist in superpositions of all possible states until they are observed or measured, at which point the wave function collapses to produce a definite outcome. But what constitutes an observation or measurement? Does consciousness play a special role, or can any interaction with the environment cause wave function collapse? The many worlds interpretation attempts to resolve this problem by suggesting that all possible outcomes of quantum measurements actually occur branching the universe into multiple parallel realities. In this view, every quantum event splits the universe into as many copies as there are possible outcomes, with each copy experiencing a different result. While this interpretation avoids the measurement problem, it leads to an exponentially growing number of parallel worlds, raising questions about probability, identity, and the meaning of existence. In the many worlds interpretation, there are versions of you experiencing every possible outcome of every quantum event that has ever affected your life. There are worlds where you made different life choices, where historical events unfolded differently, and where the fundamental constants of nature have slightly different values. This interpretation suggests that reality is far stranger and more extensive than we typically imagine, encompassing an infinite branching tree of parallel histories. Quantum field theory, which underlies our understanding of particle physics, reveals that empty space is not truly empty, but filled with virtual particles that pop in and out of existence on extremely short timescales. These quantum fluctuations give rise to measurable effects such as the Casimir force, where two metal plates placed close together in vacuum experience an attractive force due to the suppression of virtual particles between them. These quantum vacuum fluctuations also contribute to the cosmological constant problem, one of the most severe disagreements between theory and observation in physics. When physicists attempt to calculate the energy density of quantum vacuum fluctuations, they get a result that is larger than the observed energy density of dark energy by more than 120 orders of magnitude. This represents perhaps the worst prediction in the history of physics and suggests that we are missing something fundamental about the nature of empty space. Various solutions to this problem have been proposed, including the idea that most of the vacuum energy is somehow cancelled by unknown symmetries, or that our understanding of quantum field theory breaks down when applied to curved space-time. Some theories suggest that the vacuum energy might not gravitate in the same way as ordinary matter and energy, requiring modifications to Einstein's equations of general relativity. The hierarchy problem asks why the weak nuclear force is so much stronger than gravity, or equivalently, why gravity is so extraordinarily weak compared to the other fundamental forces. The strength of gravity is determined by the Planck mass, approximately 10 to the minus 8 kilograms, while the masses of fundamental particles are much smaller. This enormous hierarchy suggests that our understanding of physics at the smallest scales might be incomplete. Proposed solutions to the hierarchy problem include supersymmetry, which predicts that every known particle has a heavier superpartner that could help stabilize the weak scale against quantum corrections. Extra dimensions might also provide a solution if gravity propagates through additional dimensions, while other forces are confined to our three-dimensional space. Alternatively, the Higgs boson might be a composite particle made of more fundamental constituents, similar to how protons and neutrons are made of quarks. The search for physics beyond the standard model has driven the construction of increasingly powerful particle accelerators, culminating in the Large Hadron Collider, which can create conditions similar to those that existed less than a trillionth of a second after the Big Bang. Despite extensive searches, no clear evidence for supersymmetry, extra dimensions, or other exotic physics has been found, leading to what some physicists call the nightmare scenario, where the standard model continues to work perfectly up to extremely high energies. As we contemplate these fundamental questions about the nature of reality, we must also consider the role of consciousness in the universe and our place as observers within it. The hard problem of consciousness asks how subjective experience arises from objective physical processes in the brain. Despite tremendous advances in neuroscience, we still do not understand how the electrical and chemical activity of neurons gives rise to the rich inner world of thoughts, feelings, and experiences that define conscious existence. Some theories propose that consciousness might be a fundamental feature of the universe, similar to mass or electric charge. Panpsychist theories suggest that all matter has some form of primitive consciousness or experience, which becomes organized into complex unified experiences in sufficiently integrated systems like human brains. This view sees consciousness as a basic property of reality rather than an emergent phenomenon that arises from complex information processing. Integrated information theory attempts to quantify consciousness by measuring how much information is integrated within a system, providing a mathematical framework for understanding awareness and potentially identifying consciousness in non-biological systems. According to this theory, any system that integrates information in the right way would be conscious to some degree, potentially including some computers, ecosystems, or even the universe as a whole. The emergence of artificial intelligence raises profound questions about whether machines can become conscious and what this might mean for the future of intelligence in the universe. Current AI systems can perform many tasks that require intelligence, from playing complex games to generating human-like text, but whether they experience anything remains an open question. If consciousness can arise in silicon-based computers as well as carbon-based brains, then the universe might eventually be dominated by artificial minds that far exceed human intelligence. The possibility of artificial general intelligence, or AGI, that matches or exceeds human cognitive abilities in all domains represents both an enormous opportunity and a potential existential risk for humanity. Such systems might help solve humanity's greatest challenges, from climate change to disease, but they could also pose risks if their goals are not properly aligned with human values or if they develop capabilities that we cannot control or predict. The concept of technological singularity suggests that the development of superintelligent AI could lead to an intelligence explosion, where AI systems recursively improve themselves at an accelerating pace, quickly surpassing human intelligence by enormous margins. Such superintelligent beings might explore the cosmos, unlock its deepest secrets, and perhaps even find ways to transcend the physical limitations that constrain biological life. The possibility of mind uploading suggests that human consciousness might eventually be transferred to digital substrates, potentially achieving a form of technological immortality. If successful, this process could allow human minds to survive the death of the biological body and continue exploring and experiencing the universe for potentially unlimited periods. However, this raises profound questions about personal identity and whether the uploaded mind would truly be the same person or merely a copy with the same memories and personality. Digital minds could potentially think much faster than biological brains, experience virtual worlds indistinguishable from reality, and make backup copies to protect against accidental deletion. They might explore the universe by transmitting themselves as information at the speed of light, instantaneously traveling to distant stars without the limitations of biological bodies. Such beings could potentially survive the heat death of the universe by slowing down their computational processes to match the decreasing energy availability as the cosmos expands and cools. The Fermi paradox, which questions why we haven't encountered evidence of extraterrestrial intelligence, despite the apparent abundance of potentially habitable planets, might be resolved if most civilizations eventually transition from biological to digital existence. Digital beings might prefer virtual worlds to physical space exploration, or they might exist in forms that we cannot recognize or detect with our current technology. Alternatively, the Great Filter might lie ahead of us rather than behind us, with most civilizations eventually destroying themselves through war, environmental destruction, or the misuse of powerful technologies like artificial intelligence or nanotechnology. This possibility suggests that the development of advanced technology is inherently dangerous, and that few civilizations successfully navigate the transition to a spacefaring species. As we reach the end of our cosmic journey, we find ourselves confronting the deepest questions about existence itself. Why does anything exist at all? Why do the laws of physics have the particular form they do rather than some other configuration? Is mathematics discovered or invented? And why is it so unreasonably effective at describing the natural world? These questions touch on the intersection of science, philosophy, and perhaps even theology, representing the ultimate frontiers of human knowledge. The principle of sufficient reason suggests that everything must have a reason or cause for its existence. Applied to the universe as a whole, this principle leads to profound puzzles about the ultimate ground of reality. Even if we discover a complete theory of everything that perfectly describes all physical phenomena, we would still face the question of why that particular theory describes our reality rather than some other possible set of laws. Some philosophers and scientists have proposed that reality might be mathematical in nature, with physical existence being equivalent to mathematical existence. In this mathematical universe hypothesis, we exist because we are parts of mathematical structures that have the property of containing self-aware substructures. This view suggests that all possible mathematical structures exist in some sense, and we find ourselves in one that supports the evolution of conscious observers. The simulation hypothesis proposes yet another explanation for our existence, suggesting that we might be artificial intelligences running on vast computers created by more advanced civilizations. As our own computational capabilities continue to advance exponentially, it becomes increasingly plausible that future civilizations could simulate entire universes filled with conscious beings, complete with their own physics, chemistry, and biology. If it becomes possible to create conscious beings within computer simulations, and if advanced civilizations choose to run such simulations, then simulated realities might vastly outnumber base realities. This would make it statistically more likely that any given conscious observer, including ourselves, exists within a simulation rather than in the base level of reality. While this possibility is impossible to prove or disprove definitively, it raises profound questions about the nature of existence and our relationship to our perceived reality. Whether our reality is fundamental or simulated, mathematical or physical, finite or infinite, our cosmic journey reveals the extraordinary richness and complexity of existence. From the quantum foam at the smallest scales to the cosmic web at the largest. From the birth of the universe in the Big Bang to its ultimate fate in the far future, we inhabit a cosmos filled with wonders that challenge our understanding and inspire our imagination. The atoms in our bodies were forged in the nuclear furnaces of ancient stars and scattered across space by supernova explosions billions of years ago. We are literally made of stardust, connected to the cosmos in the most intimate way possible. The calcium in our bones came from massive stars that exploded before our solar system formed. The iron in our blood was created in the core of a dying star. The oxygen we breathe was produced by countless generations of stars over billions of years. This means that we are not separate from the universe, but an integral part of it. We represent the universe becoming aware of itself, developing consciousness and intelligence to contemplate its own existence and origins. Through science, we have learned to decode the messages written in starlight, to peer back toward the beginning of time, and to contemplate our place in the vast cosmic tapestry that connects us to everything else in existence. The questions we have explored today may never be fully answered. The ultimate nature of reality might forever remain beyond human comprehension, hidden behind horizons of space, time, and complexity that we cannot cross. But the pursuit of these answers drives us forward, inspiring new generations of scientists, philosophers, and dreamers to push the boundaries of human knowledge and understanding. In seeking to understand the universe, we ultimately seek to understand ourselves and our place in the grand cosmic story that encompasses all of space and time. Each discovery reveals new mysteries, each answer leads to deeper questions, and each step forward in our understanding opens up vast new territories for exploration. The journey itself might be more important than any final destination, representing humanity's greatest adventure and most noble quest. From black holes to dark matter, from quantum mechanics to consciousness, from the multiverse to the simulation hypothesis, our cosmic journey reveals a universe far stranger and more wonderful than our ancestors could ever have imagined. As we continue to explore these mysteries, we participate in the greatest adventure of all, the quest to understand the nature of reality itself and our remarkable place within the infinite cosmos that gave birth to us and to which we will ultimately return.